Hi, hello, welcome to last and final section of chapter 6, the exceptions to Octet Rule. And also, thankfully, this is also one of the less stressful topic. As I said, it gets easier after section 6.3. Section 6.4, 6.5, and 6.6. It just less stressful topics, which is good for you. But nevertheless, this is kind of, go along with section 6.3, the information. What we learn in section 6.3 is how to draw Lewis structures, right? We had set up total 9 rules that you have to follow first 6 and kind of use 7 and 8 and 9 rules to cross check your structure, just make sure everything is correct. And we discussed if you refer to the Lewis structure rules again, especially in rule number 2, I discussed about where there are a few exceptions you should be considering whenever you draw Lewis structures, such as, sometimes you have to choose a central atom to make more number of bonds, even though that is traditionally not known to make more number of bonds. Like I said, period 3, 4, 5 elements can make more number of bonds than it would. And other exceptions that we are going to discuss. First exception that I'm going to discuss here is that incomplete octets. If you can see it here, I highlighted it, incomplete octets. Now, one thing what we discussed is when draw Lewis structures, you have to make sure the main group elements the main group period 2 elements must have octet number of electrons. What are main group period 2 elements is carbon, nitrogen, oxygen, and fluorine. Only these elements must have 8 electrons whenever you draw Lewis structures. Let me repeat again, because if you do not follow, something is wrong or something falls under exceptions. Carbon, nitrogen, oxygen, and fluorine must have 8 electrons, except under it is discussed under exceptions. Okay, so other elements will and can have less than 8 and more than 8 and still come up with a correct Lewis structure. So first one here is incomplete octet, which means we are going to discuss about molecules that has a central atom or any atom that doesn't have 8 electrons. Excuse me. So here, the example is that the central atom has fewer than 8 electrons due to a shortage of electrons. What can we do about that? The example that we are looking at is beryllium. And beryllium, to start with, has only two valence electrons. It is from group 2, and it only had 2 single valence electrons. If at all, it is making a bond with hydrogen, close proximity electrons, electronegativity values. So it's kind of making these covalent bonds. And when it does, it can only have maximum of 4 electrons total in it. We cannot do anything about it because it just the way it is. It has less number of electrons to start with. It brings the only 2 electrons to the table, so it cannot have more than 4. Okay, and another popular example is an element from group 3A, boron. Most specifically, boron most popularly cannot have 8 electrons. Maximum it can have is 6, because boron has a 3 valence electrons because it is from group 3. So 3, when it makes 3 bonds, it will have maximum of 6 electrons, so it is short by 2 electrons. And I really like that, that boron cannot have octet number of electrons because of its nature of not able to have 8 electrons and having that room for extra 2 electrons made boron so enticing for researchers. And researchers have exploited its boron ability to have that empty pocket to take more electrons into it. And researchers have made a beautiful, highly useful catalyst. I just want to show you this to make sure I am sharing my screen. Yes. Okay. Yes. Let me show you this that I have here. Nobel Prize in 1973, that's long ago, awarded to Herbert Brown and George Wittig. Herbert Brown is the one that worked on a boron-based catalyst And while I'm looking for a few examples of boron-based catalyst, I just quickly come across this, Sigma, which is a company that makes, catalysts. They sell chemicals. See here, these are the list of boron catalysts that you see here. BCl3, and boron-based compounds, more boron-based compounds. All of these. Most of them are very expensive too. All of these are boron-based catalysts. And what do they do? They help make the bonds that are really hard to make otherwise without the help of those catalysts. Excuse me, I need to resume my slides here. Impossible. So because of the ability of the boron that can only have 6 electrons, like a short of 2 electrons, it is so interesting for researchers to kind of, tease it with 2 more electrons, dropping 2 electrons. Boron would love to get 2 more electrons from somebody, which gives away. And using that as an advantage, catalysts were made. Catalysts were molecules that help make chemical reaction possible without otherwise very hard to be done. He was awarded Nobel Prize. You can see the importance of these boron-based compounds. Again, it is possible to make all of those beautiful catalysts because boron cannot have octet number of electrons, but it would love to have if somebody gave 2 more electrons, which is what Herbert Brown did, and he got Nobel Prize for that. What do you say about that? That's win and win for everybody there. So rule number two for exceptions to octet rule is that the central atom has a fewer than 8 electrons due to an odd number of electrons. It happens sometimes, not a whole lot popular, but it can still happen. We have a single electrons instead of even number of electrons. Sometimes we have single electron as a result of chemical reactions that it is exposed to. We have radical initiation chemical reactions, and they instead of using the paired electrons for reactions, they kind of break the bond evenly and use the single radical electrons to react. So these are highly reactive material. So here what you're seeing is the free radicals, and the free radicals just happen to have odd number of electrons, and you cannot do anything about it. You cannot be picky about who is going to hold the single electron. Here it has to be a nitrogen because both the oxygens on the outside are more electron negative, and they are not going to take 1 less electron than 8 in comparison to oxygen. Remember the funny slide that I showed you in the very first time I talked about electronegativity in this chapter? Oxygen in competition with nitrogen got the extra 2 electrons because oxygen is more electron negative. So nitrogen has to hold that single electron, and it has to settle for 7 electrons instead of 8 because free radical is created. And when free radical is created, what can we do? There are no electrons to give it to anyone. And the third exception to octet rule is that the central atom has more than 8 electrons. This is the most popular, let's say, octet rule that you have to use because we have plenty of examples that you have to get used to working with molecules that has a central atom that has more than 8 electrons. Here we are going to spend some time on these kind of examples. One of the popular example is sulfur. Sulfur normally would like to have, just like its neighboring same period element oxygen, it would like to have 2 lone pairs and 2 bonds and have 8 electrons total. However, these sulfur or other elements from period 3, period 4, period 5 also happens to have empty d-orbitals in 3, shell 4, shell 5, which helps them, which encourages them to accommodate more number of bonds than they normally could, just because they were larger, just because they got extra room. Like, think about you're a student living in a 4-bedroom house, and if you are a nice guy like sulfur, you would help out a friend that doesn't have that, has no room because their room is flooded in winter. You wouldn't want to leave them alone in the cold winter in a flooded house. You would give the extra room to them just because you have the extra room, right? Just like that, sulfur has, free extra room in its 3D orbital. If there are more electrons, it's like, okay, I'll take care of you guys. I'm gonna hold you guys because I got extra room. So it happens only for elements from period 3, period 4, period 5, these elements. So just be open to that idea of these elements from period 3, 4, 5 can hold more than 8 electrons. So it is okay if they hold more than 8 electrons, right? Because it is keeping the whole molecule stable. That's that's all it matters, right? Keeping the whole molecule stable for the greater good. So they were kind of making sacrifice. So it is asking us to draw the Lewis structure of chlorine dioxide. Okay, let's work on that. First, let's count how many total electrons that you see for chlorine dioxide. The total valence electrons that you see for chlorine dioxide is chlorine has 7, each oxygen has 6. So 12 and 7, 19 electrons. So I'm looking at odd number, something kind of exception that I'm sensing here. So what is going to be your basic skeleton structure? You have chlorine and oxygen, and between chlorine and oxygen, chlorine has to be the central atom. So you kind of have to open to the idea of, considering one of the exceptions if you need to. Obviously, we are discussing the octet rule exception. So this is how your basic structure is going to look like. And you have 19 valence electrons total, but you used 4 valence electrons currently. So you subtract 4 minus 19. So you only left with the 15. And out of 15, if you look for how many lone pairs you can have, you can only have lone pairs for even number of electrons. So for out of 15, the closest, excuse me, let me get my pen. So 15 minus 1 is 14, the even number over 2. So you will have 7 lone pairs and 1 single electron. Okay, sorry, 1 single electron and 7 lone pairs. So what are you going to do with those 7 lone pairs is you're going to give first to oxygen to make sure they have the octet electrons. And if you left any in step 5, you give it to central atom. So if you do that, all 3 oxygen have 3 lone pairs, you give 1 more to chlorine, you still left with 1 more electron, you give that to chlorine. Chlorine would like to have 8, but we don't have 8, we only have 7, so we give it to chlorine and it has to deal with it because we don't have it. It is a free radical molecule, what can we do? But these free radical molecules are also useful in its own way. They were also fantastic molecules. And when you think about free radicals, one thing should come to mind is quick, fast reactions, super fast reactions. As a matter of fact, kind of more of the explosives, a lot of explosives are free radical chemical reactions. That's why they happen really fast and create lots of destruction, but not a good thing. But we just have to discuss chemistry, but why would you want to make a bomb, right? Not a good thing. But science, I'm just discussing. Free radicals. Because of free radicals, it happens so quick. Whew. But I hate explosives. So here, ClO2, just looking at the uses of the ClO2, just for your information. ClO2 is kind of, found in bleach as well. It has, uses of using it as a disinfectant, and which is very popular one. Again, free radicals kind of have the high energy single electron. What free radicals does is, we discussed partly in organic chemistry, if you take that class, free radicals are very highly reactive and they kind of can destroy molecules that it come in contact with pretty easily. For example, here they discuss one of the great uses of this ClO2 free radical molecule is They eradicated the toxic mold in New Orleans homes that were destroyed by Katrina hurricane in 2015. Yeah, it did the job because it is a free radical molecule and it can destroy mold or whatever the other toxic material is because it's kind of a badass free radical molecule. One of the other, just come to my mind, well, I guess it is fair disclosure for you to share this information. We people in general say that, don't get stressed out, your health will spoil, you shouldn't get stressed out, you should calm down, you should control your stress levels, otherwise you age fast, you lose your health, right? All of those things are true. Uh, Mainly we say that part of the reason that when you get stressed out you kind of put your body through hell physically inside that you wouldn't notice for outside, but inside what would happen is stress creates molecules that were free radicals. Stress, the cause of stress is the response to the stress by our body is creating free radical molecules. And those free radical molecules, they create ruckus inside of our body. And they kind of, break down the molecules that were not supposed to break down because, think of our body. Nothing is for waste, right? Everything has its unique properties. What do we say? Body is like a temple and you need to keep it safe um, and clean and you need to take care of it. But if you get stressed out, you involuntarily, without knowing, create these badass free radical molecules that may be good for killing really toxic mold, but not really good for our human body, not really good for our temple. What it does is it just destroys the molecules and the bonds that it's not supposed to. And as a result, one of the leading causes for the cancer is lots of stress in the body. So because these free radical molecules are randomly breaking down the molecules that it's not supposed to and creating byproduct, creating waste, and it is eventually accumulating to leading to some form of cancer. See how bad these free radicals are. So calm down. Even if chemistry is hard, calm down. You will eventually get it. Don't stress it out. Your life is more worth than just trying to learn one or two concepts. I will help you. I will help you to not to stress out. So calm down. Stress is bad. Because I told you how you would create stress and how you would destroy body. Let me tell you how you can stop it. Even if you're stressed, well, the best way is to not to get stressed out. But if at all you think you're under stress, it's not going to happen immediately. But in general, even if you're exposed to a little bit tiny stress, in general, the best practice people say is, or scientists say is, consume a lot of antioxidant-rich food. Like yogurt, my best method of supplying antioxidants to me are fresh fruits and vegetables, highly pigmented fresh fruits and vegetables. These contain lots of antioxidants and they were kind of blockers for these free radicals. We say antioxidant is good for our body because, without knowing that, we say right thing, because antioxidant stops the damage done by free radicals. How nice is that? That's why eat more vegetables and fruits. Not saying don't eat meat because I also eat meat, but just include colorful food, vegetables and fruits. So yeah, I'm happy that I shared what I know. But again, please, yeah, don't stress out. It doesn't worth it. Eventually you will learn it. You just need to invest more time. Going under stress is not a great way to learn anyway. Okay, and also not a great way to die. So yeah, please. All right, so let me discuss remaining few topics here. Draw the Lewis structure of boron triiodide, Bi3. Boron, whenever you see boron, you should have the image that, oh, it is one of the element that goes under exceptions to octet rule, which means it cannot have full 8 electrons. It would and should be happy with only 6 electrons. So boron triiodide, basic structure should look like boron in the middle, iodines outside, and if you count the total valence electrons, it should be 24. Out of 24, you made 3 bonds, so exclude 6 electrons, you left with 18, and 18 by 2 is 9 lone pairs. You have to use those 9 lone pairs on each side of the iodine, so 3 lone pairs each. So you would come up with Lewis structure like that, and you don't left with any more electrons, which is the way it should be because boron cannot have more than 6. Okay, this is the Lewis structure. Okay, let me pause and remind you what I told you before start of this chapter. I told you that at the start of the chapter, and I showed you that, image of molecules, atoms coming together, making bonds. I told you that you will get really good at drawing Lewis structures by the end of the chapter. This is kind of by the end of the chapter. We just have a couple more problems. I'm talking to you like you were a pro too, right? I'm not trying to go to each step here because by this time you should be good in drawing Lewis structures. If not, it is time for you to practice more, okay? Because I'm considering you as a pro, that's why I'm just going with the words instead of trying to walk you through by each step. That should be a Lewis structure. If it doesn't make sense why it should be a Lewis structure, you should rewatch the video, section 6.3, or talk to me immediately. Okay, either way is fine with me. Here are a couple of alternatives of moving electrons and writing resonance structures, and this is also fine. Just showing that whenever there are electrons nearby, outside electron, like iodine has lone pairs and central atom has no octet rule. What it does, it will share electrons. So which is nothing wrong, right? That's what we do it in step 6 of Lewis electron rules, except that we don't have to do it for boron because it is already happy with 6 electrons. Okay. So draw the Lewis structure of arsenic pentafluoride, AsF5. So arsenic is an element not from period 2, and you have 5 fluorines next to it. Carbon, nitrogen, oxygen, fluorine cannot have less than 8 electrons except under special circumstances like radicals, which means arsenic has to hold more fluorines by itself. It got to step up and help the friend fluorine. Friend fluorine, nice rhyming, I like that. Oh, so arsenic is being the central atom, and it connected to 5 fluorines. And if you identify the location of arsenic is from group 5, so it has 5 valence electrons. Fluorine is from group 7, so it has 7 valence electrons. There are 5 fluorines, so 35 valence electrons, and plus 5 valence electrons of arsenic, total of 40 electrons. Here for the bonds between 5 fluorines and single arsenic, you used 10 electrons, so you left with what, 30 electrons. 30 over 2 is equal to 15 electron lone pairs. You know what do you have to do with these lone pairs? You would start creating double bonds. So if you start you would start making lone pairs to give the octet to most electronegative element, which is here clearly fluorine outside. Each fluorine currently has 2 electrons, so they need 3 lone pairs each. There are 5 of them, and you have 15 electrons. So if you start giving these 3 lone pairs to each fluorine, you would end up using all the electrons that are available. So that's how the arsenic is going to end up with holding 10 electrons instead of 8, and it is fine because it is able to create a molecule, AsF5, instead of creating much less stable molecule. Arsenic is just taking extra 2 electrons, and it normally don't have any problem with it because it has extra room in the form of the orbitals. That's why they were able to take those extra electrons. Just a couple more problems before we wrap this chapter. Draw the structure of xenon tetrafluoride. And xenon is not from period 2, larger element. Fluorine has 4 electrons. Let's see how we end up with. So it is the basic structure. Obviously, fluorine cannot have more than one bond. It is from period 2. So if you count the valence electrons, xenon is from noble gas group 8. And when it gets larger, even noble gases are exposed to bonding, especially really large elements. Xenon, I guess, has like 54 electrons or something, so really large. So it doesn't really matter for xenon at the time if it has to participate in bonding or not participate in bonding. It is fine either way. So xenon is shown to interest in participate in bonding. So it is using its 8 valence electrons, and 4 fluorines has 28 valence electrons. So 28 and 8 is 28 and 8 is equal to 36. So you used 8 valence electrons for bonding there. So you left with 28 valence electrons. 28 over 2 is 14. So you have 14 lone pairs, and each lone pair here need 3 lone pairs. And if you arrange them, you're still left with the 2 lone pairs. And what do you do with those 2 lone pairs? You give it to the central atom, because fluorines cannot take more than 8. So you ask the xenon to take the extra load of electron. So it doesn't matter 8 or 12, xenon is still able to take those extra electrons because it is from period 5 or 6. I think period 5. Okay. All right, just a couple more problems before we wrap this chapter. So it's asking us to draw resonance structures of H2SO3. The one that obeys the octet rule for the central atom, and the one that minimizes the formal charges. Not really. I looked at the solution that we got here for the textbook. I don't really think that one obeys the octet rule is the right way to say. I think the question wanting to say one that has formal charge, one that has minimal formal charge, one that has a larger formal charge. Because I looked at the 2 answers, none of them is obeying octet rule, both of them going under exceptions. But neither way, you got sulfur, oxygen, and hydrogen, and which one should be your central atom? Sulfur should be your central atom, because sulfur is from period 3, can accommodate more elements, and it comes with the practice. Sulfur loves to connect to oxygens, but not hydrogens. Some chemical reasons, and hydrogens love to be on the oxygen outside, which eventually going to make them act like an acid, which we will discuss a lot in third term of this general chemistry sequence. So when it does, if you rearrange remaining electrons, you would end up with either this structure where you have formal charges of -1 and a +1, even though sulfur has more than, or sulfur has 8 electrons still, and sulfur has 0 formal charge, 0 formal charge, 0 formal charge, 0 formal charge. But here on the top molecule, we got charges. That's what question is asking, not the one that obeys loose structure rules such a way. Or I guess it is asking us to try a loose structure that has least formal charge. I guess question could be asked much more clearly. So this is the least favored structure because it got charges, and this is most favored structure because it got neutral charges. Okay? When you draw loose structure, you should draw a loose structure that has at least formal charges. All right, very last slide, last exception to the octet rule category. The elements that are not able to gain the 8 electrons through normal bonding would love to participate in coordinated covalent dative bonding. You can call them as either dative bonding or coordinate covalent bonding to form a Lewis acid-base complex process. Again, Lewis, he did so much contribution. I don't know how he never got Nobel Prize even after nominated for 41 times. It's still on my mind. So Lewis again proposed the complexes called Lewis acid and base theories based on the molecules that cannot follow octet rule attacked by molecules that has extra electrons to make a new bond. So this bond actually should look like an arrow to correctly represent, because electrons are coming from nitrogen to boron. So here, electron deficient, BF3 is electron deficient and NH3 is electron rich. Electron deficient molecules are called as Lewis acids, and electron rich molecules are called Lewis bases. So here, Lewis base attacked Lewis acid to give 8 electrons to boron, and it forms complex, and it always forms complex. Again, the sigma-rich compounds that I showed previously, if you remember, almost all of the molecules has boron 8 electrons in it, because when it is time, they go back and attack something else, because it is easy to break the bond with the boron. That's how they were useful in such a way. And even nitrogen here can break its bond any way it wants to, because it is its own pair electrons. It's kind of, all of these molecules are taking the advantage of boron neediness. At some level, we kind of have to feel sorry for boron, but on the other side, it is helping us making so many fantastic synthetic molecules. So yeah, well, thank you, boron. All right, and with fun chart, I'm in a good mood because this is my last slide. How awesome is that? This is the summary of everything that we discussed in this chapter. Every one of these words are making sense to you. Congratulations to you. And that is how normally it should be. And if some of the topics are not making sense, and if you feel like you forgot some topics already, you just need to revisit those, topics again, watch the videos, or talk to me. But it is possible for you to master these topics with, watching these videos maybe multiple times, or getting help from me, or through practice. I'm telling you, it is entirely possible for each one of the students to master this topic. Just go through them slowly, follow the rules, try to make flashcards, because all of this information looks easy when you hear it for the first time, but it is very easy to forget about them if you don't, come in contact with them constantly. So I want you to keep your mind fresh on these topics by revisiting them for every day or every couple of days, so that you would develop this familiarity. That's what key for this chapter and next chapter. Just need familiarity. You constantly need to review and review and review. And one thing that happens, even to really good students, is, well, it happens to every chemist in general, not just the students, even the professors. If we don't, come across the same topics for months, like large summer break or large Christmas break, we kind of feel a little bit rusty for, first couple hours. Because that's what chemistry is. Unless you practice, it's not like, it's not like throwing a ball. By heart, right? You can easily do it. It's not like that. It's a mind process. So if it's happening to a professor his job is to teach, it would most likely happen to you as well as a student. That's why you need to keep it fresh. You need to recycle, review, recycle, refresh, practice constantly, because that is how you master these topics. And thank you for watching all of these videos, and give me your feedback if you have any. I'm going to take it to make the better videos next time. And I hope you enjoyed learning these topics. I certainly enjoy teaching this, because Lewis structures and electronegativity are some of my favorite topics. All right, bye for now. I will see you in the chapter 7 lectures.